second day of the boot camp. Today we have two speakers again in the morning, Kathryn Schaffer and Donald Hoffman, and I'll introduce them separately in a minute. And then we have the same format later. We have an open session at 1 o'clock, and then at 2 o'clock, the workshops will start, the math camp with Michael and Jakub, and then Natasha will run the same workshop she ran yesterday, again this afternoon. The other thing that I wanted to emphasize is that when you're asking questions, when you're writing your questions up in the webinars, please use the Q&A function rather than the chat function, because I think that will make things easier, although we'll see how it goes. So I think that's all in terms of bureaucratic stuff. So why don't I move on to introduce Kathryn. And Kathryn actually is a repeat. We haven't invited too many people back, not because we didn't like the people we have, but because we really, really wanted to spread things around. But Kathryn gave a talk last year, and I'll get to that in a second. Just first, the basic introduction. So Kathryn Schaffer is an associate professor of physics at the School of the Art Institute of Chicago. So that means her students are design and art students, and she's teaching them physics. So I thought, when I came across Kathryn, I thought this is perfect for quantum social scientists, because we probably know as much about physics as the art students do. So last year so I should finish the introduction. So her experimental physics background includes research in neutrino physics, nuclear physics, and cosmology. But starting in 2016, she began a collaboration with another physicist, Gabriela Barreto Lemos, and they've written a lot of papers together. And through that discussion, Kathryn's work has moved into the whole interdisciplinary discussion of the connection between quantum theory and humanities, social science, and actually art and music. And so last year, Kathryn did a presentation on quantum theory and art. And it was actually far and away the most popular presentation afterward when we did the course evaluation, so to speak. And Kathryn's presentation and the seminar was the one that everyone loved the most. So we thought we had to bring her back. And then when I asked her to come back this year, initially I thought she could do the art presentation again, but she proposed doing one on music. And I knew there was a literature on quantum and music. There's a literature on quantum and everything, but not a lot. But so I thought this would be, I have no idea what to expect, but I thought it would be a great idea. I did want to mention one other thing, actually, with regard to Kathryn's collaboration with Lemos. There's a terrific article, one of the best articles that I've ever seen that kind of summarizes quantum theory for a non-expert audience. It's called Obliterating Thingness, and it came out in Foundations of Science in 2021. And maybe at some point we'll put it in the chat function so that you can see the citation. But it's a great article if you need a one-stop shopping kind of, here's an overview of quantum theory. It's a good place to start. So I'll leave that. And I think I've said everything I wanted to say about Kathryn up front. The title of her talk is Quantum Music on Metaphor and Meaning, and I'll give it to the floor to Kathryn. So thank you.
Thank you, Alex. As last year, I am joining this from a farm in Northwest Illinois. And last year I was worried about the Wi-Fi, so I sent in a video recording. I didn't do that this year, which means the Wi-Fi might glitch out, and you might need to tell me that I need to say something again. So please be ready to do that. Before I share screen and get started, I want to thank Alex and everyone for organizing this. It's a really interesting conference and boot camp and introduction to quantum physics, but also for people who've been following interdisciplinary quantum ideas for a while. The conversations are pretty rich, and I really enjoyed it last year, and I've been enjoying it this year. Also really appreciate that you do this remotely. A very big focus of my life, which has basically reoriented my life, is trying to do direct environmental action as much as possible in my life. And I really appreciate when we can make a conscious choice to do something that is a lower carbon footprint than business as usual. So I really appreciate these virtual conferences, given that the world has just experienced the hottest week on record. Okay, so let me share screen and get this rolling. Okay, you should be seeing my slides. Is that look okay?
Yes,
And you can hear me okay so far?
yes, so far.
Okay,
Mhm.
so far so good. Okay, good. Please interrupt me if needed. So I'm going to talk about quantum music. I'm actually going to talk mostly about that paper, that obliterating thingness that Alex mentioned. And I will be using music as a way to talk about the main themes of that paper. I want to note that just the introduction was fantastic. And as of today, I am still associate professor at the School of the Art Institute, but I have just submitted my resignation, in part for lots of reasons, but in part because I am really trying to consciously spend as much time as possible on climate issues. So just note that for the future. I don't know where that will land me in terms of future work, but it was the hottest week on record last week. So here we go. Okay, so last year, the approach that I took for this boot camp was I talked about a fictionalized example of an art critique. So I kind of made up or semi-fictionalized example of an artwork and talked about the critique process in a art school kind of context to articulate some metaphorical connections between art and quantum physics. Yesterday, both talks yesterday were very heady, very interesting. Harold Ottmansbacher had an example, the artist Boys, that captured my point from last year really beautifully, that art itself, contemporary art, and especially performance art, often muddles the subject-object distinction in really complex ways intentionally. It often engages multiple sites of agency. It's hard to locate where is the art. Is the art in the object? Is the art in the act of experiencing it? Is the art in the mind of the artist or the mind of a critic or a particular audience? It also manifests in an unavoidably partial and contextual manner. This is especially true if we're talking about performance or music. This example was articulated yesterday. It's sort of the example that I used last year in presenting that art kind of has this metaphorically quantum character. It exhibits a number of the same features as physics on the quantum scale. So I'm not going to focus entirely just on that point again. And a difference from last year is that this year I'm going to gesture towards some actual sound art in music works. Last year I used a made up example. And I was worried about trying to manage all the files and get all the audio clips to work. So I'm not going to share the actual audio clips. I'll describe some of them. But if you find this interesting, you're going to need to download this PDF later and click on the links and go listen to them because it's music, it's sound art, and it needs to be heard. Okay, so I'm going to talk about quantum music, sort of. As if it's a thing, and as Alex said yesterday, quantum social science also isn't just a thing. There's a lot of different discrete directions that fall under that same hashtag, as it were. But I wanted to start off with just noting that, as someone with a physics background, we're kind of always in a defensive stance because quantum everything is everywhere and it's terrifying. Quantum toothpaste is a thing at this point. And so it's like a stressful experience for most physicists to enter quantum anything as a thing because how do I know that you're talking about something more sophisticated than toothpaste? And in particular, there's this whole world of associations that seem to come with the quantum hashtag, quantum everything, that we're going to do something new. It's going to be revolutionary and profound and deep, discipline-defying, mysterious, authoritative, because it's science, beautiful, holistic, spiritual. All of these kind of feelings and expectations seem to come with the word quantum. And you can tell that this has there's a thing there. There's a if I were an AI and I wanted to mine the internet for quantum everything, I would come up with a coherent set of ideas and a coherent aesthetic. This is just an image search that I did on Google for quantum everything, and there's an aesthetic. So it involves bald people. And I want to note that even the image for this conference follows up with that. The bald people and the swishy lines, that's quantum. That's how you know that you're dealing with quantum something. Okay, so I'm a little bit personally allergic to this. I see this and I have the same response that I do to quantum toothpaste, which is, oh no, where are we going with this conversation? And so I kind of like to counterbalance it by saying that most of my own encounters with interdisciplinary quantum everything are actually quite authentic to individual intellectual disciplines. And I think that's a good thing. Usually what's happening is discipline-specific goals are being articulated and advanced. If quantum is being merged with something else, social science or music, it's often because it's a good title for grants and conferences. And then hiding underneath that is normal mathematical modeling, well-established approaches, science proceeding the way that it normally does. Humans liking to connect with each other and get other input because we've always liked to do that. We don't, intellectual discourse has never actually been completely siloed off. We always talk to each other. Creativity functioning in its normal ways, and people like novelty, but we're still advancing the disciplines. Of course, I say that, but then I thought, well, I'll see what an image search on interdisciplinarity looks like, because I kind of have this feeling that, like, we've been doing interdisciplinary discourse for a long time. It's not really new, but this is an even more awful set of aesthetics. So I don't know what to make of that. So I'm going to tell you a bit about quantum music. I participated, so as if it's a thing. I participated in a couple of conferences through pandemic times, hosted in Brazil, that followed up on a particularly large and well-funded project in Europe that began in maybe 2016 and has had several iterations since then. So I'm going to report on some of the things I heard about at those conferences, as well as share some of what I shared from this or at those meetings. If you read the websites and the funding agency pitches, they, of course, promise some kind of revolutionary newness, a new discipline of music. The reason I think it's interesting, as someone who is also an amateur musician and amateur sound artist, is because it's good experimental music. It's interesting experimental music. It's not because of some novel new discipline. It's because it's doing what musicians and artists do well, with something interesting to work with. So that's my opinion. And I will note that there is also an aesthetic to electronic music and experimental music, the sort of that just happens to be one that I like a little bit better. So maybe it's just as generic as the other sets of ideas, but this suits me better personally. Okay, so as if quantum music is a thing, and as if quantum social science is a thing, I guess you can interpret what I was just saying as a move towards kind of unthingifying it, recognizing that we're really invested in disciplines because they structure our goals and thoughts, and I think that's valuable. And my anti-thingification is consistent with being a co-author of this paper, Obliterating Thingness. And I am going to stick more closely to this paper and its content in my presentation this year than I did last year, because I think it has been really useful for a lot of people encountering quantum ideas for the first time, and I'm really glad about that. And I hold on to this as a really useful thing that we did, and I think you'll find it useful if you take a look. Okay, so Obliterating Thingness was pitched as an introduction to the what of quantum physics, as well as the so what of quantum physics for other fields. And we wrote it. Gabby is the true quantum physicist of the collaboration, but we wrote it with my students, my brightest art students, in mind as the audience. So let me summarize some of its key points. Focusing on quantum physics as a discipline, the discipline of quantum physics, it is a thing people do who call themselves quantum physicists. What is that? Well, first of all, it has a scope. Physicists who are identifying as quantum physicists are studying light and matter on the subatomic scale, the things that are called quanta, electrons and photons and so forth. Okay, that means if you encounter a quantum physicist on the street, they're not thinking about philosophy. They're not thinking about the mind-body problem. They're not thinking about music. They're thinking about electrons and photons. That's the scope of what they do. It has a form. And this is really important because the form of so the form by which I mean the form of the content of the discipline, the knowledge content, what form does it take? this is different. Physics is different from the fields represented by many of you, in that the primary content of our discipline is not language-based. It is encapsulated in empirical facts and mathematical models. Yes, we use words. Yes, we use all kinds of drawings. We use all of these tools, but we argue a lot about exactly how to express things in words. Where we don't argue is when we're looking at data and equations. Those are the domains of consensus for physics knowledge. Those are the forms of the knowledge, the forms that it takes authentically within physics. All right, and it's a discipline, it has practices. Those practices are experiments, and experiment means something really different in physics than it does in music. In physics, it's a rigorous, repeatable thing. Lasers in a controlled environment, vacuums, things like that. There are mathematical derivations associated with the interpreting the results. We make research publications like any other field. And then there's a whole spin-off of technological applications, and we all are using them. We're using our phones and computers right now, and they're based on quantum physics in very direct ways. Okay, so this is a summary characteristics of quantum physics as a discipline, and the most important thing here is that it has no philosophy that is a consensus part of this picture. And I'm going to just say this, and I'm going to drill this home a lot of times. There is no consensus ontology associated with this body of knowledge or its practices. It's arguably to step into questions of what it means, what it really means, or what are electrons really, what are the photons really, how is it that we're working with mathematics to model the world. All of that really arguably steps out of physics. And there's an overlap region, which includes people like Christopher Fuchs, who spoke yesterday, where people with the physics expertise are kind of searching within the equations and within the data for information that would let us make those kinds of statements. But there's an enormous amount of debate. And from the consensus standpoint of there's a discipline, it is not a discipline that explains what an electron is. It just doesn't do that. It uses the facts and the models, but it doesn't tell you what are quanta. Why are they like this? Why do they do what they do? Okay. All right. So if you're coming in from another field, social science, music, art, anything else, and you're going to borrow something or take inspiration from something in quantum physics, the ontology isn't part of the physics. So what can you borrow from the physics itself? You can borrow, well, all right, everything in the world is made up of electrons and photons and stuff, so maybe that's relevant. That's kind of comes along for the ride always. You can borrow some of the information, some of the content of the field. You can borrow some of the facts of the empirical experiments. You can borrow some of the models, the mathematical structures. Or you could use possibly the technology. I mean, we all are right now. We're using the technological spin-offs of quantum physics. So those are the things that you could take. You could from outside of quantum physics. Okay. So again, I'm kind of framing this in terms of how we express it in obliterating thingness, and I'm characterizing that these are the kinds of things that are available for pulling out of physics and using elsewhere. Okay. So again, I'm going to reiterate that the difference in form is really important. The facts and models of quantum physics in physics are not best captured in language. We use words like entanglement. We talk about complementarity. We talk about contextuality. But it gets really difficult to pin those words down because the words are not really the core content. The core content is we're using those words to describe experiments and models that have a correspondence to those experiments. So to talk quantum physics like we do in conferences like this is usually to commit ontology by accident. Usually, if you force a physicist to communicate about quantum physics outside of their research field, they're going to fall into some kind of a philosophical worldview by accident. And it's not necessarily because they actually are committed to it. So just know that. Acknowledging that talking quantum physics is usually to commit ontology by accident, I like to capture the essence of quantum physics, if there is one, as non-thingness. A key insight from what we've learned about nature is that the concept of a thing, an object, doesn't always work in every context. Okay, so a thing, so just really casually characterizing this, a thing is an object. It has a well-defined place, it has well-defined boundaries, it has a trajectory, it has a history, I can tell a story about it. A thing is like my phone, it's here. It has edges, it's not over there. If it moves through space, it goes continuously, all of that kind of thing. All of those features are characteristic of things. That's what I'm trying to say. And what I mean by non-thingness is defined in the negative against those features of things. Non-things are entities that lack well-defined place, well-defined boundaries, well-defined trajectories through space and time, well-defined histories. They typically require some consideration of context. They typically engage distributed agency. You cannot consider the phenomenon, the entity, without considering the impact of the environment, in addition to agents within the environment. And every story that we can tell about a non-thing is necessarily partial. There isn't an expectation of being able to get the entirety of what is there, because it is actively engaged in different ways, in different contexts. Okay, so physics shows, and this is one way of talking about core results in the field of research quantum physics, that quanta, meaning electrons, photons, atoms, resist being described wholly as things. Sometimes they can be, in some situations in physics they can be, but they resist that as a complete discussion of how they work. And last year, I used art as a metaphor to argue that works of art also resist being described wholly as things. Thus, art can be a way into quantum insight. And again, I said this already, but just to reiterate the basic idea there, think about a music performance. Where is it? Is the music performance only where it happens, or is it separately experienced in the minds of every person who is there? If you looked at the score of that musical performance, does that contain a piece of it? If you took a recording, does that contain part of it? How does the concert hall or the basement or wherever, how does that participate in the experience? Art has intrinsically a lot of features that are in common with the non-thingness of the quantum scale. Okay, this connection that I'm drawing here, to me, is metaphorical. I am using art as a metaphorical way in to thinking about non-thingness. That is the move I am attempting to make. Okay. All right, so quick check of time. And please interrupt me if audio is an issue or if anything else is an issue. All right, again, I've characterized that these are the things that we can borrow from quantum physics and use elsewhere. So what might you do with that? What's the so what of quantum physics for other fields? And obliterating thingness, again, is pretty surface level. It's intended to be an introduction to these ideas. So there's a great deal more depth represented in the talks at this conference. But it's just a starting point. Here's my characterization of some of the obvious so whats of quantum physics for other disciplines. A really obvious so what is, it just doesn't matter. Who cares? If you're not dealing directly with the electrons and photons in your phone, you really don't need to know how transistors work. Like, you just don't. And that's true for, a lot of what we do as people and as thinkers. You might work in the domain of metaphor, like I was just doing myself, that working with the facts of quantum physics is very generative in terms of expressing metaphors for other domains of knowledge. I am going to make a point that I've tried to make in previous talks, and I feel like it's the one kind of really contentful thing that I'm trying to contribute here, which is models are metaphors. Models are also a form of metaphor. If you borrow the mathematics from physics, you are also committing metaphor. That is what is happening in that move. So I'm going to group those things together, kind of playful conceptual metaphor on the one hand and a model-based mathematical metaphor on the other. Those are metaphors. It's also true that as we go forward, building technology on the basis of what we learn in quantum physics labs, that technology becomes available to use and to interrogate, to critically assess and encounter in the world. If you would like to look into physics and take something worldview-y, something philosophical, something that influences your approach as a thinker, you do have to take a step beyond the physics. You have to make some kind of an ontological commitment. And as I was excited to see that this year's version of the Bootcamp has a whole special afternoon session on Kathryn Barretto's work. Kathryn Barretto's book, Meeting the Universe Halfway, which is what I've put along the bottom of this slide, is by far the most common way to make them common. If you did like a literature survey across every field that publishes academic work, by far the most common resource that people have used to take some kind of a worldview from the quantum world, quantum physics, and move forward outside of physics is drawing from Kathryn Barretto's work. Kathryn Barretto has kind of fills this in. So you can't ask a physicist how should I fill all this in and what worldview should I have? But you can ask Kathryn Barretto and you can get an answer. Okay. Oops. All right. Okay, so let me apply these ideas for music specifically. The so what of quantum physics for music. Most of music is in the I don't care category. Most music you can make and enjoy not thinking about the electrons and photons, even if they're involved. Okay, oops. So let's talk about specific quantum technology. A lot of music actually uses technology developed through quantum physics. Transistors, for example. As a hobby, I build guitar pedals, and I'm really into the vintage germanium transistors from decades ago. That's all quantum physics, which I am using to make really crazy, raucous guitar sounds. But these days we have quantum computers, and a really important discussion in the social science space, or I hope it's a really important discussion, is thinking about the ways that quantum computing will revolutionize warfare and cryptography and various other state level issues. You can also use quantum computers for music. So that's a thing. And are people doing it? Yes, they are. There, you can find some of this. You can listen to it. This is a screenshot from a video of a performance of some sound artists who are using a hand control of a something called a block sphere. It's a mathematical entity that is relevant for quantum computing. And basically, as they manipulate as they move their hands, they're essentially manipulating the digital representation of the block sphere, and then that is being piped to a synthesizer to make sounds. What does this sound like? It sounds like experimental music. It's like whoomp, 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 and bzz kind of sounds. That's what it is. It's doing experimental music with quantum computers. Okay. And actually go listen to it, because it's really interesting. I'm not, my womp womps are not catching it. Okay, so you can do that. You can do the technology thing, use new technologies to make music. And, by analogy, maybe new quantum computers are going to be important simulation engines for social science research. That would be an analogous way that the technology might come into play. Okay, most ways that music is going to use quantum physics, and I would say most ways that social science is going to use quantum physics, are metaphors in some way. There's some metaphorical translation of facts or translation of models. Okay, the biggest quantum music project that I know of is in that space. And it's very interesting, and it's been going on for a number of years, and it's what was reported at some of the conferences that I attended. it's partly it's been so successful because the two main people involved who are collaborating directly with each other are both big names, and they're really good at what they do. Kim Helveg is a composer, and Klaus Molmer is an extremely famous quantum physicist. And the two of them have actually actively worked together, funded under some European creative arts funding initially, and then several other funding cycles to work together on making music that in some way engages quantum physics. There's a really nice, relatively recent article on this in Aeon. So if you want to read about this project, that's a great place to start. And it goes through a lot of the general, it's written by a young physicist, and thus kind of expresses the caution that physicists feel when they encounter quantum music or something else. So their work they've produced a number of music pieces and sound art pieces and conferences and performances. Many different aspects or many different projects have come out of this this collaboration. And I want to just highlight two of them in order to make the point about different types of metaphor. Okay, so obviously in a creative space, conceptual or playful metaphors are really important, drawing from anything for the creative process. An example of how this, of sort of a conceptual and playful metaphor in this particular collaboration is in this piece that Kim Helveg composed called Superposition, Many Worlds. And it's written up in this musicology paper, and I'm using the musicology paper to describe it here. So let me make sure that I can read this. This is from that paper. This was one of the earlier collaborative pieces that these two worked on under their quantum music project. And as I understand it, it involved a musical composition for two pianos that were also coupled to some electronic devices. But part of it was inspired by the quantum mechanical phenomenon of spectra, of atomic spectra, in particular the Lyman series, basically quantum ways that nature itself, that atoms themselves have sort of a fixed set of frequencies that they can express. Those frequencies expressed quantum mechanically are frequencies of light, but in a sound context, you could certainly think in terms of similar types of frequency relationships in sound. But the work itself, in this case, was not attempting to be that mathematically rigorous. It was interpretive and creative. I'll just read a little bit of this description. The prelude is based on short chromatic motif consisting of 4 notes. At its first repeat, it is expanded to 5. Constant repetitions with minor modifications of the motif create a trembling musical line in the first piano, while the second piano remains silent until it is awakened. It is as if the movement of the first particle in the first piano has kickstarted the second particle to react in the exact same way. Hence, at its first entry, the second piano faithfully copies what the first one did. The two pianos, i.e. particles, then start to interact. And so on and so forth. It is as if we can witness the transitions and emission lines of the hydrogen atom. This is metaphor play. It's a very interesting piece of music. I mean, you can get clips of this. You can find some of the documentation, but it is not attempting to directly translate, represent quantum information in sound. But the same people did do that kind of work. And again, I really want, like, if there's one thing that I feel like I'm adding that isn't just sort of surface level in description, it's really that it makes sense to think of models as metaphors. Models are math, and mathematics is a type of metaphor, in my opinion. Any kind of modeling or cross-domain representation that relates to the structures in quantum physics is also a form of metaphor. And another project that came out of this same collaboration involved literally taking measured vibrations of a quantum system, in particular something called a Bose-Einstein condensate, taking those vibrations and using them as sound. Okay, so this might be a little bit harder to follow in a way, and I won't read as much of it, but in this set of projects and pieces, a Bose-Einstein condensate is a state of matter on a quantum scale that is created and manipulated in very elaborate systems like this. It involves vacuums and lasers, and it's not something that makes sound. Like if you were standing here when it would make the sound of all the machines and things whirring, but the Bose-Einstein condensate is a very tiny, tiny material thing. It vibrates, however, and as those vibrations are recorded with a camera, those vibrations can then be transferred from vibrations measured visually to vibrations heard sonically. And that is exactly what this aspect of the collaboration involved. So what they did was they used a common piece of software in experimental music called Max MSP, and they basically input all the numbers, all the math of the vibrations of the Bose-Einstein condensate and use that to make sound. So quantum acoustics is a thing, studying the vibrations. Acoustics in physics means vibrations. Studying the vibrations of Bose-Einstein condensates is a thing. And in this artistic context, what they have done is literally take that and make sounds with it. So that's a thing too. And it's a really natural direction to go to explore the structures of quantum physics through sound, because there are really natural mathematical correspondences between these two domains. Okay, so quantum math involves waves. The image on the left is quantum scale resonances in an atom. It's an illustration of mathematics. The image on the right is a photograph constructed to illustrate the vibrations of an instrument. There are natural mathematical correspondences between these. I can use the same equations to talk about atoms and guitars. That's how that works. Again, I really want to emphasize that mathematics is kind of a form of metaphor. Math is about structures. It's about identifying common structures, and we have to pick which structures we're going to focus on and which we're going to represent. But then we can make these structural comparisons, and we can make encodings and translations on the basis of those structures. Just as a really simple example, I can have a set of 4 heads of garlic. I can also have a set of 4 emotional responses to something I saw on Instagram. There's some way in which a set of 4 is a common structure between these. So maybe that's a relevant way to think about that. I can think about 4 emotions and 4 heads of garlic, but they're also really different in that my set of emotional responses might have a really different meaning if it's reordered, whereas my set of garlic heads doesn't have a different set of meanings if I reorder them. Garlic is obviously a very arbitrary choice here, but I just harvested like 200 heads of garlic and I have to go peel them after this. So this is why it's on my mind. Anyway, beyond a set of enumerated objects, mathematics is really not so much about counting. This was a point that was made yesterday. It's about structures. And within physics, the structure of waves is used all over the place. We use wave physics to talk about light, to talk about sound, to talk about water, to talk about earthquakes, and also to talk about probabilities in quantum physics. We use waves everywhere. And just like with the very silly example of garlic and emotions, there are structural similarities between all of these systems that enable us to kind of compare and work across domains. There are also structural dissimilarities. There are actually ways that water doesn't behave like sound. There's ways that light isn't the same as an earthquake. There are both commonalities and dissimilarities at the same time. But because of the commonalities, there are so many ways that if you know this math and if you know this physics, that you can see connections across different domains. This is another silly example that I picked sort of arbitrarily. There are really, I've used this example in classes a lot of times in different ways, but mathematically, there's a ton of similarity between what's happening in your microwave oven and what's happening inside the pipes of a pipe organ in one of the great cathedrals. So if you're ever in a cathedral or in like a really, someplace that has like a really spectacular pipe organ, as you listen to those incredible sounds, you can contemplate microwaving your lunch. There's a commonality there between the mathematics and those two different contexts. I could have chosen, if I'm trying to make the point that waves are everywhere and therefore we can draw these correspondences and cross-domain representations, I could have chosen much more exciting seeming comparisons. I could have chosen to tell you that gravitational waves are, can be sonified into things that you can hear. I could have told you the way that the entire universe shortly after the Big Bang was like a musical instrument, analogously, analogous to a guitar, essentially playing the future of galaxies. That's a super fun conversation. Would those things have come across as deep, profound, spiritual, universal, beautiful, all the things that go with the purple switchy things and the bald heads? It might have. Probably lunch and church doesn't, but that's kind of my point. The math is metaphor. Waves are everywhere. Okay. In technology, in particular in the technology that, well, in all kinds of technology, but in the technology that we use for art and experimental music in particular, we do this all the time, where we take math and translate it across structures. And there's nothing especially new in this. It's the foundation of old school radio. Old school radio takes sound, records it with a microphone, makes an electronic image of the sound, an electronic wave that represents the sound wave, then imprints that information on light waves, which is the radio. So if this kind of transfer of structures from one context to another, if we think of this as deep, well, it's kind of everywhere, and it's kind of like microwave ovens are related to pipe organs deep. It's lunch church deep. If we think of this as something new, then what we mean by new is been around since we started inventing any form of technology. It's what we do. Okay, enough with the editorializing on that. So my point here is that math is this form of metaphor in my take on things, and waves are everywhere. The same logic does apply in a quantum physics context and in a quantum interdisciplinary work context, because waves are involved, first of all, but contextually sensitive, order-dependent effects of the kinds that are modeled by quantum mathematics are also present in different contexts. It's similar to microwave ovens are like pipe organs. You can use the same math in both contexts. You can also use similar math to talk about the probability of quantum events and the probability of human decisions. Okay, that's the comparison I'm trying to make. Okay, and my final, I'm running a little bit over, but I think I can do this in about 5 minutes. So I want to do one final move here, which is to take the Karen Barad step and go ahead and get into worldview and ontology and show what that might look like in a quantum music context. Okay, so this is a step beyond physics. This is a step into worldview and into thinking into potentially going beyond the metaphor if you take on a Baradian philosophy. Okay, so we're going to try this out, and hopefully if you attended the workshop yesterday, some of the vocabulary here might be more comfortable at this point, thinking about matter, meaning, entanglement, and so on. Maybe not, I don't know, it's hard. I'm going to use an example by the artist and composer Alvin Lucier. And this is really famous. And it's like, if you study sound art or performance art of, people encounter this and they discuss this piece a lot. It's a really, really important work. Okay, and this is a quote from Alvin Lucier. Every room has its own melody, hiding until it is made audible, which relates to the very famous piece, I Am Sitting in a Room, which was first composed in 1970. And then there were many performances and recordings that were made by Lucier and also others. The concept of the piece, or the way that it works, is that Lucier would sit in a room on a chair in this kind of configuration and read a text into a microphone. The sound would be recorded in a device, a tape recorder, and then played back into the room, and then re-recorded and then played back in. So after the first iteration, so he speaks the first iteration, but after that, it's being played into the room by a device and then re-recorded. When you do that, you are listening to the sound in the room, and the room is having an effect on the sound. Here's the actual text that he read, and if you listen to this over many iterations, the sound completely changes. The very first iteration, you hear his voice and his words articulated. Over time, as the room and the environment interacts with the sound, it transforms into something that sounds more like a harsh electronic feedback. The text is here, and it's very self-referential. He is reading, and then the work is reiterating. I am sitting in a room different from the one you are in now. I am recording the sound of my speaking voice, and I'm going to play it back into the room again and again until the resonant frequencies of the room reinforce themselves, so that any semblance of my speech, with perhaps the exception of rhythm, is destroyed. What you will hear then are the natural resonant frequencies of the room articulated by speech. I regard this activity not so much as a demonstration of a physical fact, but more as a way to smooth out any irregularities my speech might have. And that was a relevant move for Lucier, the artist, who had a stutter. And so as you hear this, there's typically the irregularities in his voice, which are then over the course of the work smoothed into these strange tones. Okay, so, oops, I guess I do have this on here. I don't know if that's coming through. I'm not going to play it because I'm short on time. Okay, so in principle, this is coupling in the room in the creation of the piece in a very explicit way. Lucier says, every room has its own melody hiding there until it is made audible. In a metaphorical quantum-y kind of way, the piece clearly engages context, is clearly engaging that kind of non-thingness of art. There's multiple agencies, the space matters. It also engages a performance of the artist's own identity and stuttering speech as a feature of that. There's conceptual quantumness everywhere. But I also want to note that physically, there's a lot going on too. So what's actually happening in this piece isn't just listening to the space. It's true that sound resonates in rooms, and that rooms like concert halls are designed very specifically to control the acoustic effects of the space. But in this particular piece, actually quite a lot of the sound that emerges is the devices. This was actually studied in like an acoustics research paper, which is linked here. An awful lot of the reason why the sound is shaped iteration after iteration into these really strange tones that it becomes is actually just because of the microphone. It's because of all of the resonances and the physical effects, many of which involve quantum scale physics, all the way through the entire, electronics, the system. Okay. And the positioning of the room, everything, all the specificity of making the piece matters to how it actually sounds. If you move the artist and the recording devices to a different location, you might get a different sound. If you have an audience, it physically matters. If you have a lot of people in the room, it will dampen the sound. It will change the way that the sound works. It might even change the temperature. And if you change the temperature in the room, the speed of sound in the room actually changes, which will change the resonant frequencies of the room, as well as the objects in it. So on a physical scale, there is so much participation in making this piece from physics on all kinds of scales and related to the people involved, related to the room, related to the devices. So one might argue that actually the sounds are not nascent in the room. It's not listening to the room. They emerge in the full experience of this specific piece in a specific context. Bodies are participating, minds are participating, devices are participating, walls are participating, the structure of space and time itself participates. And there's a conceptual side of this, the metaphorical side, maybe, that, why do I say that minds participate? Well, does it even count as sound art if no one hears it? Cultural, material, economic context matters, like how expensive is the microphone is going to matter. But there's also a physical sense in which all of those same things matter because of how the sound is materially generated. So I would argue that this is a really good example of the Karen Barad move. there's no clear dividing line between these two ways of thinking about contextuality and entanglement in a sense. So the Barad move would be to say matter and meaning are entangled. We can't really isolate completely the conceptual side of how we analyze this work and the physical side of how we analyze it. We could also say maybe we're just working with a more complex set of metaphors. Okay. If you don't want to take a full ontological leap into agential realism and say that everything is the same on all scales, maybe it just means that we have to be a little bit more careful understanding the metaphors when we cross scales. Okay, that was probably kind of a subtle point. I'm going to wrap up because I'm running a little bit late. Do I have a way to tie this up? Let me summarize what I said and then make some final points. So primarily, I summarized what's in that paper, Obliterating Thingness, in which we try to situate quantum physics as a discipline and discuss the fact that it does not itself provide a worldview or an ontology, and then discuss some of the ways that you can borrow and that people do bits and pieces of it, not for toothpaste, hopefully, but for creative work or for interdisciplinary work. My key point that I want to constantly emphasize is that models are not necessary. Mathematics doesn't necessarily give you meaning. Mathematics is a form of metaphor, and it's a form of identifying structure, and modeling is a form of identifying structure. And thus, borrowing the models from physics doesn't get you to ontology any more than borrowing the ideas does. So those were some of my key points, and I used some examples from music to illustrate different ways that people borrow ideas from quantum physics, but this is also common across the social sciences and other fields too. Okay, so then I actually want you to do stuff. Really what I want you to do is save the planet. Like, it's not okay that this was the hottest week on record and it's going to get worse. But okay, in the context of this conversation, if you're new to quantum social science, read the paper as a starting point. I think it has shown that it works. And what I've talked about today is mostly in the last section. If you find the music and art examples in this talk interesting, I really do want you to go check them out because I did not characterize them in the depth that they deserve. So go listen to them. When you encounter quantum something as a hashtag, ask about is it a metaphor? Is there a claimed ontology? And if so, then it's definitely stepping beyond physics. And I would like to add, again, if you see math, or if math is referred to, it's a clue that it's metaphor, not a clue that it isn't. It's a clue that metaphor is involved, that there's some kind of a structural correspondence, like the structural correspondence between microwave ovens and pipe organs. Spend some time with Barad. Barad's work takes time, but it's good stuff. And if you're focused on the apparent success of some quantum inspired models in social science, I'm sure this is where I'll get into arguments with people later. Compare the situation to my lunch and church analogy. But also, this is something that I've been thinking about and writing about with my collaborator, Gabby, and we have an upcoming paper, which, watch for it. In it, one of the things we try to do is articulate some of these points about mathematics and models more carefully. And then finally, because I think this was kind of informal and has lots of points, please argue with me later at 1 o'clock. And I will I'll end there and bounce out, and we can see what happens.
All right. Well, thank you, Kathryn. And I'm glad you mentioned, so it sounds like you can attend the 1 o'clock open session. Excellent. Okay.
Yeah.
That'd be great. Okay. We had, so Michael or Joyce, which one of you did we decide would be moderator?
I will help.
Okay.
Yes. So, hello, everyone. Thank you, Kathryn, for the wonderful talk. So we have, if you can click the question and Q&A session down there, you might see. So first question is from David Orwell. Hey, Dave. Dave was one of our speakers last year, if you remember. So here, Dave asked one question. Great talk.
Yeah.
That using methods first developed in quantum physics means making a metaphor with physics. But if we use a classical computer to model something, this is not exactly the same as metaphor. Because, for example, we can use a model to make accurate predictions. Similarly, if you use a quantum computer, we can do the same. So it doesn't mean we are making a tortured comparison with subatomic particles. So my question is, if social systems show properties such as interference and entanglements that are amenable to a quantum treatment, then can we model them at face value without invoking physics at all? Isn't that a main question, whether the method work or not?
Yes. Hi, David. I haven't seen you in a while, but yes, absolutely. And so thank you for forcing me to articulate the point more carefully. Physics doesn't need to be involved at all. All right. So the points, the sort of torture points I'm trying to make are in response to a thing that has been said in past conferences of this sort, which is, wow, you can use mathematics borrowed from quantum physics to model what happens with human decision-making and brains. Okay, what I'm trying to say is that's like microwave ovens and organ, church organs. The same math works in both places doesn't mean anything about a connection at all. It's just whether the math works. That's exactly what I'm trying to say. It's just whether the math works. But what the paper that is forthcoming, what that addresses is there is a step past that, which is more subtle. And if you push me on it, I'll probably start to get, it'll get difficult to express. But there's a more subtle question about what modeling does in science, not just in physics, but in science in general. And that, engages a bunch of philosophy of science and thinking about representation and explanation much more rigorously. And the point I will make is that, in my opinion, this is a philosophy of science statement representing a part of my stance. In my opinion, it's not completely the same kind of science or scientific reasoning that physics does if all you're doing is identifying that a model is predictive. Because what I believe science adds beyond mathematical description is explanation. So I'll give a specific example to make the point that I'm trying to make so that it's more clear that a friend of mine who used to work in AI in the earlier days of image recognition made this point by saying that the first AI engines that they asked to sort images of people's pets into cats and dogs came up with a predictive rule that dogs are green. Okay, so you can get the predictive rule that dogs are green from the fact that most people take pictures of their dogs outside. So that's really good, like a quantitative rule for a computer to use to predict whether, or to, assess whether an image is a dog or a cat. But it doesn't address the why. And the why is where I would identify science coming in. So when we talk about mathematical models that are borrowed from physics being used in economics, if they work, they work. That's all we have to say. There's no connection to physics. But I would also say there's another layer of understanding the why, which is where the really rich scientific questions come in. I don't know if that made sense, but hopefully.
Thank you. And here, by the way, tomorrow's talk by Professor Emmanuel Pathos and myself will give some example about this. Emmanuel is there on the panel list, and myself will show some examples how we try to model some of decision tasks and some cognition tasks. Again, there are different levels of involvement of concepts, but there are the use of the mathematics. Thank you. And Robert D, he said, can you send the links? But I guess this I can address that we will have maybe PowerPoint and video available online on our webpage. So there. And of course, you're welcome. I think at 1 o'clock, maybe Kathryn can even play some of those links for us.
Yeah, I could load them up and see if that works.
This is a totally different experience than you sit on your farm and listen to it.
Yeah, but I have a feeling that probably the next talk is going to raise a lot of questions. And so I'm kind of hoping that the 1 o'clock session, we get to talk about that. But we'll see.
Have the music, the background. This is totally
We could do that.
Now, David have a second question asking, can quantum social science help solve the climate crisis? We are all hoping for that, right? So, okay, that's my hope. By changing our mental framework, such as by changing our mental framework.
Wow. I mean, we should talk, like, we should ask this of other people. You shouldn't ask me because I'm really, really cynical right now about changing mental framework as a way of changing things because it hasn't worked. So I don't know. I feel like one thing that we know is that, okay, one thing that I think I know is that a lot of things in education and the way that we've gone about it for the last 20 years have actually been kind of the same. Like, I sort of feel like the things I teach my students are pretty similar in a lot of ways to what I learned. It didn't work then. We didn't fix this, and we knew. So I don't really have a lot of faith that our continuing attempt to educate in the way that we do is a key player. And I think that makes sense just because, you know, we get very wrapped up in our academic world, but we're not the world. So, I mean, that sounds really negative. I do like the flip side to it, which is that, which is more personal, is that if you push me on it, like, why have I left academia at this point, and why am I on a farm doing the things that I am? I'm thinking about Kathryn Barreto constantly. It is very much a move to think about multi-species agency, posthumanism, action in the world, and causality. The newer paper that that Gabby and I worked on is about causality. And I mean, as a person, I think constantly about causality because I'm making a lot of conscious actions in the environment in an attempt to build bumblebee habitat. And I'm trying to do so in a way that avoids some of the problems of past interactions with the environment. So I'm personally kind of a cynic on the mainstream, change the world through changing ideas line. At the same time, I draw from all of these ideas all the time. So.
Thank you. I mean, this is really a big question, deep question, because the quantum physics have changed the world. But like, if we're doing quantum social science, whatever, then so what, right? Like,
Right.
what
Yeah.
do we? Oh, okay. Alex had hands first. Then we'll go back to the Q&A. Then Matt has a question. Alex, would you like to ask that?
Yeah, I just wanted to comment briefly on will it change the world and solve the climate? I actually believe yes, if we teach people to think of themselves as quantum beings, but that's sort of a separate point. The question I wanted to ask actually was about metaphor. And I get this a lot when people, hear me talk, this is just a metaphor and so on. And that's okay. I understand the critique. What I always wonder though, is the alternative default classical model that all my colleagues are trained and I was trained to make and so on, are those also metaphors? Because they're usually treated as if this is real and the quantum stuff is metaphorical. And so I'm wondering if you would accept that, or do you think both are metaphorical? And then where's the ground that we're standing on, in a sense, if everything is
yes.
So
yes, that. I think that's also metaphorical. And I think that's responsive to how it actually functions in physics too. And I guess that, and that's, I'm trying to summarize what we wrote in the paper that isn't out yet, so you can't see it. But in physics, if I take physics and I kind of do, as like a really solid example of how, how science works with models, because that's what we do. We build models, mathematical models. There really, in the practice of physics, there really is not a either or classical quantum divide. That just doesn't exist. It really isn't like that at all. And I mean that on a lot of different levels, in that an electron in some situations can be modeled with classical mathematics. An electron in other situations requires quantum mathematics. So that's one way to make it really simple. But another way to say it is that if I take the devices, the material things that are made and used, a transistor is a good example. A transistor functions on what we would say is essentially quantum stuff, essentially quantum processes, but you don't need to know any quantum modeling to use them at all. You can model what they do in a very simple mathematical way. So from the standpoint of models, it really isn't either or ever. And thus, yeah, I mean, that's the main thing. It's not classical versus quantum.
Well, could I just follow up really quickly? I mean,
Yeah.
but at least in social science, we are trained to model always in classical terms. We're not even they don't even tell us about the alternative quantum models, right? So it's classical logic, classical statistics, classical probability. So that's creating, I think, a de facto ontology. They may
Which
not
is
call it
right.
that.
Yeah, but that's like right, but that's not something that physics does.
Right,
That's
okay,
what I'm
physics,
that's what I'm
but
saying.
I guess I was responding
Yeah.
to the situation in social science where that's
Right.
kind of the
Right.
challenge.
And sure. And the way, so, but then people will look at physics and say, yeah, but you had the quantum revolution and now you do everything in quantum terms. We don't. We use the right model for the right, in the right context. And what decides what the right model is? I mean, it's a very painstaking, there's a lot of philosophy of science there, but it's a very painstaking thing. And it, that causality matters. Like explanations matter. Why it is that way matters. Yeah. And that's ultimately going to help you know whether it's the right model. You have to know why it works that way.
Joyce, go ahead.
Okay, so this is a very great question, and I hope like tomorrow we can continue with this with Emmanuel and my talk, and to exactly, I think there are different ways even in cognitive science, and many of us like doing this kind of model even have different views about how much ontological concepts of theories we have to be committed to, or we don't have to. So we will see. Now we go back to Q&A with Matt has a good question. I think exactly asking a question as a person in social science, or at least someone studying human behaviors, maybe social behaviors. So do you have a stance on what it is we do when we perform empirical inquiry? For example, there is a gray line between observational studies and controlled experiments. I guess this here means like in the human studies. And in both cases, we attempted to identify the outcomes or consequences of our actions or measurements. Settings such as this can be made more precise, but how?
There's actually, I mean, there's a lot of questions in there because there's, deeply in there is the full-on philosophy of thinking about, epistemology. But from a practical standpoint, you're a social scientist and you're working with modeling and you're studying things. I think what I'm arguing is that it's causality and probability. Those are the two words that I would really focus on. A rigorous understanding of the mathematics of probability and its commitments and its implications, and alternative ideas about probability. Alternative is wrong because if social science has assumed that probability is one exact way only in the past, that's probably a mistake. Probability is more complicated than that, and the theory of probability is more complicated than that in mathematics, for sure. So I guess that is what, rigorous statistics, really good statistics, understanding statistics is what I think is really important. And then within the context of rigorously understanding statistics and rigorously understanding the types of causality that are possible and how they relate to statistical results, that's a pretty good guiding point for any type of work, whether it's quantitative or more observational and less formal. It's the statistical inference, like what kind of a conclusion can I draw from the information that I've received, really depends on understanding statistics and causality at a more deeply than a surface level treatment.
Yeah, very interesting. This is really a big question actually for those of us who do this kind of work in social behavior science, and it's really have conceptual, but like psychological conceptual kind of intuitions, but also it's always up to some empirical test. And sometimes it's developed in the special context in social studies. And we hope to maybe share some of the work we do. It's important. Now, Eva King had a question. If math models are more metaphoric, is there a better way to find the quantum? Why in social science?
I love that. Modeling isn't, okay, so modeling, I'm going to express this. Modeling is a how. That's how the model, the math itself is a how description. It's a structural description. That's the sense in which I'm saying it's metaphorical. And that isn't intrinsically a why. That's kind of my point. So how do you get to the why? That's science. That's the experiment. Like that's the interrogating. It's the intervening. It's the changing. It's the setting up of controlled experiments or the finding of natural experiments. And that's very, very context sensitive and different in each case. I think, how do you get that? That's like all of science and study science and the methodologies of science and the philosophy of science. But I think what I'm just trying to say is that like the model doesn't bring it by itself. The model doesn't bring the why. The why is like, how do I know, why a transistor works? I'm not going to know it by the way that it works in my circuit. I have to do stuff. Like I have to change it. I don't know if that was a start to addressing the question, but
why in social science? I guess partly also feel like social science needs it. Maybe that's Alex and quite a few people's feelings here also from the social, maybe who work with social sciences. Well,
but you need what?
We need the quantum, maybe, but why?
I see.
The quantum, we don't know exactly. As Kathryn, I agree with you. We don't ask why. Maybe sometimes it is. Like
sure, right, and like you can ask it is in the same way that the AI can figure out that dogs are green. I mean, that's to know why is a really different level of understanding.
I think yesterday, Chris Focus also mentioned this, like blah blah. Why? We don't know why. It's so wrong, but then it is. Yeah. But okay, so these are really good questions. And if there's no more from the Q&A, I guess, is there any more? No. Okay. So then, is that time? Any questions from the panel? Or
we've got a few minutes still.
Yeah, a few minutes. We can.
Michael looks like
Michael has a question. Okay.
Yeah.
Oh, there's another one. See, I know this. When you're asking this question, the measurement had an effect. Then people starting to pop up questions. Okay, Michael, can you?
Yeah, interesting. So I don't too much have a question, but I just maybe have a comment. So you start a beautiful talk. I loved it. And can you hear me? Because okay. I just have maybe a comment. You started out with what is a thing and what is not a thing, and the way. So just a comment with coming with my Buddhist background, also looking deep into these things is. Both the thing and the not thing you described and you characterized, it's still a thought from a Buddhist point of view. So it's also important to look at this. I mean, we as academics, we are so lost in our thinking, and and then seeing what is not okay, what we are pointing at is not this, sure, but it's still a thought. And what is when we go beyond the thought? And I think to address things like climate change and so also to go a bit beyond the thought towards the intention and our attitude, how we operate in this world is important. But it's so we can have maybe the best model of the ecological system, and then we may fall into believing that okay, if we tweak this pathway, this is how the climate will change. Is still thinking the attitude. Our personal attitude, being content, what you do, like in your lifestyle, you demonstrated, is so important. And it's invisible, but it affects the world deeply. Yeah. So this is one thing.
Yeah.
And the others, I mean, you can comment on this maybe.
Well, I do if I can, but I don't want to interrupt you. No, I love that point, and I really appreciated. I really appreciated in the discussion yesterday afternoon. Harold did a really nice job, in my opinion, of sort of articulating the Eastern-Western difference in a way that didn't fall into reiterating the categorization that we have a tendency to do as academics. And I guess what I would add is, that's partly why I wanted to make the caveat that, like, if you speak about quantum physics in words, you're already going to jump into an ontology, and it's going to be, in a sense, in our academic tradition of categorizing and negating and analyzing in that way. And perhaps a way to look at quantum physics, and this is, perhaps something that that I draw from more in my everyday life, is the humility of the fact that we have a system of processes and scientific methods and models that work really well, but we really don't understand them, and we can't talk about them in words in a way that we all agree. And that's stance of not knowing, and is a type of humility. That's how I feel it. And I think maybe that, I don't know how you would respond. I guess I'd be curious.
I mean, exactly. I mean, this relates absolutely to a Zen attitude of not knowing is the most important. Proper Zen practice. We don't know. And honest science has exactly this attitude. We don't know, so we keep looking. We don't give up. So, and it's in this process of wanting to know, but in a very delicate way. It's not a type of greed or so. It's really just curiosity, and because you see that you're participating, your way of looking at the system changes the system. This is, in a sense, my takeaway from quantum mechanics, and this can be applied to the way we interact in this world and we transform this world. So the not knowing as attitude, very important. And the second thing I wanted to make is you rightly say the model doesn't answer the why question, but and the model, each model is just a tool which has been found by like an artist. It's like it has been like this. I wanted to make this point. This model doesn't just appear. It's not the Schrödinger equation out there. It has been chosen by somebody who has carefully looked at it, and this is the art. And this is where I think your talk also meets quantum physics. Like it's an art to choose a very simple model from the right model class, but this is always outside of the box. So the model will describe something within its realm, but there's like the act of choosing involves the intention, and it involves something from outside. So you will always have these hierarchies of boxes somehow.
Yeah, well, and I think yesterday Chris made the point that, I think it was Chris that made the point that often in actual experimental work, what you're doing is hammering on the reality until it fits the model. Like you're shaping what you set up so that you're testing so that it is really well matched by the model, so you can test something very specific. The model itself is like the actual practice of sort of empirically based science is just really hard to characterize. That's why philosophy of science is like a thing.
Thank you.
Yeah, I think the question left on the Q&A kind of touches the same question, actually. I wonder if our bodies are so overwhelmingly classical and our thinking is so embodied that quantum ontology is just a count. Count feel like the count maybe can feel like they offer explanation of causality. The why always feels like it's missing from quantum models and thoughts.
Oof, I mean, okay. I'm going to say one thought on the why always feeling like it's missing. There's always going to be a why that's missing, especially in physics, because we're never really going to get to the why Big Bang and why all that. Like, I mean, at least I don't think so. Like, there's always going to be a step beyond what we do in an empirical field like physics and in terms of the why. That's my opinion. But to the point of our bodies being overwhelmingly classical and our thinking so embodied, I'm really personally very interested in that. And I'm interested in the statement that or the notion that those things would be related, that an embodied experience would be a more classical experience. I actually think it's kind of the opposite personally. I think an embodied experience is much more of a quantum-like experience. Because if you're really thinking about the interaction between the body and the mind, it's hard to separate, like, it's hard to, some of my thinking happens in my fingers. And so really focusing on my embodied thought processes, I think, is actually a much more complicated and non-classical approach to thinking about ourselves, that for some reason we've been trained not to do. I'm going to say one more thing while I have the floor on this, because it's a piece of personal experience that has been very insightful for me, is having a baby and going through the experience of being two bodies in one. And the way that is an embodied, the embodied cognitive exchanges that are a part of that process, but also infancy. Before infants, when they're very, very small, they don't actually have a sense of their body as being separate from the world. And I've often speculated and discussed with my students that perhaps babies have a more intuitively quantum understanding of things because they have not empirically separated themselves. They haven't gone through the concept of object permanence, the concept of a body having a boundary.
Actually, can I just weigh in on that briefly? I'm wondering if you have been following the whole growth of quantum biology, and what do you make of that in the context of these discussions? Because the quantum biologists seem to be finding some really interesting stuff. I'm not sure whether they're realists about it, but it's different than social science, and so I'm just curious.
Do you mean, so quantum biology could mean a bunch of different things, but in particular, like with birds, magnetic
plants,
sensing,
and other
plants,
quantum effects.
Totally. Yeah, no, I mean, that makes sense, of course. But again, like the same way that your transistor functions on the basis of fundamentally quantum effects, yet how it works in the circuit is not necessarily governed by quantum math. How a bird's navigational system works can easily it's the way everything is. Like, we all function on the basis of quantum things doing quantum stuff all the time, but that's not always the model that is right for describing the particular system. And so I think that's, yes, of course.
Well, but I think that the quantum biologists are saying that they're finding non-trivial quantum effects.
Well, I don't understand what trivial and non-trivial would be. I really don't. Because again, like, it's just not that simple. We don't have an either or, like, I don't know. I mean, it's not that transistors are not trivial. Like, it's not a trivial quantum effect. It's a real quantum effect. But then once you know how it works, that's not the math that you need. It's like,
I don't know what kind of math the biologists need, but they seem to think that they're finding something really important that is not describable in a classical vocabulary. So I don't know what to make of that. I'm not a biologist, so.
I totally think that's, sure, like, because sensing, like vision depends on quantum processes. We know this. And so, like, yes, there's a lot to learn about it. And it's really exciting and very cool, but but
that sounds much more realist than a more metaphorical kind of way of thinking. Vision really
sure, it's realist. But so you use the really is quantum phrase, and I have a problem with that phrase. So I'm not going to fall into using it.
Okay. We'll leave it at that.
Yes.
Okay.
I have a very quick maybe comments follow up with Alex, and also actually David Orwell was mentioning the first comments as well. I guess for some students, this is also kind of what was Alex was suggesting just now, that it's not that we're trying to have to make sure the social science is quantum, but actually maybe something even more than quantum, like something like this, something beyond just like quantum physics does. And but with that also saying, like, it's because compared to what we have, the tools, the other metaphors we have, and other language we have, and this is a very good tool, at least as one way to try. And then there are ways we can empirical test whether it works better than other metaphors,
Yeah.
works better than other kind of languages we have available right now. Or
Totally.
models.
Yeah, that totally makes sense. And, you know, the mathematical step in, you know, the mathematical workshops that are always part of these boot camps and everything, I think that's amazing. Like the mathematical step is a step towards a more complicated set of ideas about probability, which is incredible. And is probably like, it makes complete sense that that would be a logical next step. But I wouldn't necessarily expect the final mathematics to be exactly the same way that, you know, if you really dig into it, the microwave oven follows a slightly different you know, set of constraints than the pipe in the pipe organ. So also, like, I think when you get, you start with quantum physics based models, but it's probably not going to end there. It's probably going to end in something a little bit more nuanced and situation specific.
And if we feel like those social questions, human questions are important to study, and then we just have to find the best way we can address some of questions, and this sounds a really wonderful tour. And actually we do find in some of our even very limited work so far, it's really enriched some of the theory as well, because we have so much more complex situations. If you don't just agree with which you know, think as some physicists, social science, pseudoscience, like it has its very, very unique challenges, like climate change. You can't just go into neurons and figure out it. There are way more than that. Yeah. Thank you so much. I think our time is running, and last call for question. If not, then maybe
No,
there's something just popped up.
The question. Look at this. You know, this is the last chance. Dr. Jolie asked, I think it was last year that you said everyone should contemplate the double slit experiment later every day, which is a story I tell a lot as an example of how science produces all quants that lead to transformation. As a student of religion, it's that sort of transformation that interests me. And I think the quantum metaphor is a great basis for transformation in our academic context, but I think it's important to remember that the concepts are support for the possibility of insights and transformation, but don't themselves lead directly to a sort of change we're saying is needed for the climate crisis, for example.
I love that. And yes, I sort of, I didn't put the double slit back in my presentation for this year, but like, you should, like, I think about it all the time. And it is that just sort of brain changing experience. And I love that. And I love that whole comment. And I don't think there's anything else to really respond to, except I just want to say that like, we have a tendency to think that all of academic work is in what we think and how we talk. A lot of it is to do with money and who funds us and how they fund us and in what contexts. And to me, when we start asking like, what do we need to solve the climate change problem and other issues, I don't understand how to address that solely through ideas without addressing the material and economic structures around the ideas. They're pretty important too. So just my own.
Thank you. Before I go to see another question pop up again, but before we go to that, I want to quickly comment, maybe again, as a little like showing like how much me as organizer with Alex and Michael like appreciate those many different perspectives on this, because as religious as Michael and Alex, like they appreciate so much about this level of transformation. I think we discuss a lot ourselves sometimes, and. But tomorrow, for example, I think I'll add back my very first empirical study inspired by the double slit experiments, showing actually maybe beyond this metaphoric change. And there are ways, even just in our real, very small empirical, pragmatic way, we can use those kind of ideas to change people's thinking and the way they think about respond to actions. But yeah, very interesting. Philip Allison asking, speaking of metaphor, it seems to me that the human mechanism works on an analog basis. This is I'm sorry, but right, it's like that. Quantum, analog, or digital.
Yeah. Right. So this question is like a fun one to take up in an experimental music context, because Roy is working with kind of well, analog and digital technology is like a discourse. So how do you think about the human mechanism? Is it analog or digital? Can it just be both? Because sometimes, because there's a certain, okay, let me try this out. And then I know I only have like 10 seconds. So if it's a failure, we can talk about it at 1 o'clock. Action, when we act in the world, has a certain digital quality to it. A thing happened or it didn't. Something definite occurs. So I think that that's like really critical as a way of thinking. Like, I think that the fact that we can represent so much of the world through ones and zeros in computers is not meaningless. I think that matters. At the same time, it's not the full story because Fourier transforms. Let's just do that. So it's not that simple.
All right.
I totally didn't answer that because it was
That's
impossible
you
in
ran
10
out of
seconds.
time.
Come
now.
back at one.
Well, thank you, Kathryn. That was really interesting, really terrific. I'm glad you can come back at 1